So sometimes we have well-behaved functions. Some other times, they are not so much well-behaved. To find the limit, our focus is on, for now, two variable functions. To find the limit of a two variable function, z equals to f of x and y on the given domain, if you have a well-behaved function, one, if z is a polynomial function, like z equals to x squared, y cubed minus x cubed, y squared plus 3x plus 2y, if your function is a polynomial function, then simply plug in x and y values. Okay. For example, suppose this function is given to you. If I ask you to find the limit at 1 and 2, it's very simple. What are you going to do? You're going to just plug in 1 for x and 2 for y. So here, the limit of z as x and y approaches 1 and 2 is going to be the limit of this polynomial function, x squared y cubed minus x cubed y squared plus 3x plus 2y as x approaches to 1, y approaches to 2. Simple substitution. Here you get 1 to the second, 2 to the third, minus 1 to the third, 2 to the second, plus 3 times 1, plus 2 times 2. After simplification, the limit is equal to 11. So, the limit of this well-behaved function, this polynomial function, at 1 and 2 is z equals to 11. So far we don't have any issue. Here you have a nice function, polynomial function. By plugging the values, you can check to see if the function has a limit or not. Second example, not so much well-behaved functions, especially when it comes to rational functions, like this scenario, like this case. Suppose the function z is given to you as x squared minus y squared divided by x squared plus y squared. Well, I ask you to find the limit. Check the limit, find the limit, or try to analyze these types of functions. Analyze the limit at, guys, in this case, take a look at this. You are dealing with the origin, 0 and 0. At the origin, 0 and 0. Okay, so let's see what we have here. When you have a function, the very first step for you is to plug in the values. So don't forget step 1. Step 1, substitute. Try to substitute. Sometimes you're lucky. Sometimes when you plug in the values, you actually get a number, like this previous case. Okay. So I'm going to follow step 1. Limit of x squared minus y squared divided by x squared plus y squared. as x approaches 0, y approaches 0, as we know, is in indeterminate form. We are unhappy here, indeterminate form. It doesn't give me anything. So from step 1, I don't get any useful information here. Okay, so what is the next step? Since I have two values here, let me forget about the second value and just enter the first value, which is 0. If I plug in 0, what do I have? The limit of x squared minus y squared divided by x squared plus y squared. X approaches 0, and I'm going to fix my y. I'm going to later on send my y to 0. For now, I'm just plugging 0 here. This is going to be negative y squared over y squared. After simplification, I get negative 1. Okay, what if my y goes to 0? I have two scenarios. X is 0, y is 0. So they are approaching to 0. Limit of x squared minus y squared divided by x squared plus y squared. Now my y goes to 0. What do I have? I have x squared divided by x squared, which is 1. I'm getting two different z values. This is my first z. Z is negative 1. This is my second z. They are not the same. Z values are different from each other. So what's the meaning of that? It means that the function doesn't have a limit at the origin. So let me erase this part. Since I have two different z values, so the limit does not exist at the origin. So you can just use the method of plugging values step by step. The very first value 0, the second value 0, one by one. Check to see if you can simplify your function. If you can simplify your function, you're lucky. Sometimes it works. And then you get two different z values. So since z values are different from each other, the limits are not the same. It means that the limit doesn't exist at 0 and 0. Some other times you can use other methods, general paths. Instead of just plugging some values, some specific values, you can plug in some regular and general paths. Let us make it more interesting. Now take a look at this example. In this example, I ask you to analyze this function. Z is given to you as x times y divided by x squared plus y squared. Okay, and analyze this at the origin, 0 and 0. Very well. So let's follow the steps. Step 1, substitute the values into the function. Okay. The limit of xy divided by x squared plus y squared. As x goes to 0, y goes to 0. This is 0 over 0, which is indeterminate form. It doesn't give me any useful information. It just says that, hey, if you directly plug in 0 and 0, the outcome is 0 over 0. Okay, I cannot do anything. This guy doesn't give me any useful information. Let me go to step 2. Now let me separately enter these values. Limit of xy over x squared plus y squared. As x goes to 0, this guy gives me 0 divided by y squared, which is 0. Okay, what should I do with the y on the denominator then? If I plug in y equal to 0, this guy gives me 0 divided by x squared, which is 0. But what should I do with x as x goes to 0? So this method doesn't work. It doesn't tell me the limit is equal to 0. Guys, So what's the next step? What should I do here? You can use a general path. Use a general path. Use a path that passes the origin. 0 and 0. Okay, I'm going to move along that path. All of the x and y values are on that function. What that path, what that function look like? In general, you have many options for that path. So in general, your path can be any of the following. That path can be y equals to mx. It can be x equals to my. It can be y equals to square root of mx. It can be x equals to square root of my. It can be the third root. It can be the fourth root. It can be in the form of a quadratic expression, mx squared, or many more. Depending on your function, guys, remember that you're trying to use these to eliminate one of the variables and make your function to have just one free variables. So the purpose, let me write it here. The purpose of using a path is to eliminate one of the variables. Of course, if you don't have extra variables, you can easily go back to elementary calculus and actually calculate the limit easily. So the purpose of using a path is to eliminate one of the variables to simplify your function. That's the whole purpose. So by inspection, you're going to select the best path that make your function simpler. In this example, by inspection, we try to find a path, or we try to select a path. Select a path that simplifies the function. So for example, if I use a square root, it doesn't simplify my function. Let me try using y equals to mx. To use y equals to mx. Any line passes through the origin. That's the meaning of these two lines. Y equals to mx is a collection of lines, a lot of lines passing the origin. Okay, I'm going to try to use this y equals to mx, which is a collection of lines. Can I simplify my function using this? Does it help me to get rid of y? Z is x times mx. Wherever I have y, I'm going to use y equals mx to try to simplify. X squared plus mx squared. This is mx squared on the numerator divided by x squared plus m squared x squared. Wow, guys, I have mx squared divided by x squared, 1 plus m squared. So my z becomes m over 1 plus m squared. This is my function after simplifying. So if I take the limit of z as x goes to 0, this is going to be the limit of m over 1 plus m squared. There is no x here anymore. It means that it is just a constant. The limit depends on the slope of the lines. This slope can be anything, so it doesn't give me a unique value. The limit depends on m, and m can be any number, just the slope of collection of lines. So there is no one limit. There is no unique limit. So limit does not exist. That's the reason behind it, that the limit doesn't exist. So again, when you're using general path, you're selecting, you're choosing a path that helps you to simplify the function. If you select, for example, radical, it doesn't simplify the function. It just creates something more complicated for you. So by inspection, you need to select the path that works the best for your function. Another example for you. So in this example, we're going to look at this function. So here you have the function x y squared divided by x squared plus y to the fourth. Okay, very good. We're going to analyze the limit of this function at 0 and 0. So let us follow the steps. Step 1, first plug in. Maybe you're lucky, you get a nice number. The limit of z as x goes to 0, y goes to 0 is the limit of x y squared divided by x squared plus y to the fourth. X goes to 0, y goes to 0. Well, this is 0 over 0 indeterminate form. It doesn't give me any useful information. So let us move on to step 2. In step 2, let us just set one of these values equal to 0, one at a time. So limit of x y squared over x to the second plus y to the fourth as x goes to 0. So here you get 0 divided by y to the fourth. Is it 0? Limit of x y squared over x squared plus y to the fourth. Y goes to 0, 0 over x squared is a 0. So it doesn't give me any useful information, all right? It just says both of these are equal to 0. You're going to use a general path to make sure you have a correct answer here. So what path simplify this function? Is it y equals mx? Is it x equals to my? Is it y equals to mx squared? Is it x equals to my squared? Is it y equals to square root of mx? Is it x equals to square root of my? And many more. Which path help us to get rid of one of these variables? Which function, set of functions? These are they all having m. It means that you have a set of functions. Which set of functions that passes the origin help us to simplify z? Which one you select? Okay, you might say that, well, here I have the option. I have x y squared, I have x squared y to the fourth. They have different power, they have different exponents. So if this guy was something to the fourth, then I could simplify this a little bit easier. So if I select x to be, for example, my squared, I can get rid of my x. And let us select x equals to my squared. Why not? Let's try. Then my function z becomes xy squared divided by x squared plus y to the fourth. X is m y squared times y squared divided by x squared. You have exponent 2, so you're going to have m y squared to the second power plus y to the fourth. Pure algebra. There's nothing calculus about this. So here you have m y to the fourth divided by m squared y to the fourth plus y to the fourth. So my function z becomes m y to the fourth divided by y to the fourth parentheses m squared plus 1. I can cancel out y to the fourth, y to the fourth. So my z after simplification depends on m. So the limit of my z as x goes to 0, y goes to 0. After simplification, we can becomes the limit of m squared plus 1. Guys, remember that we got rid of x. The function has only y in it. So y goes to 0. This is m over m squared plus 1. Since we have many options for m, since we have many options for m, it means that the z is not unique. So the limit at the origin does not exist.